this set of notes, we're going to continue to discuss sampling distributions, and in particular, we're going to look at some common statistics that you've probably seen before, and we're going to talk about their sampling distribution, as well as how this relates to the normal distribution, as well as what is known as the central limit theorem. Alright, so for this section, we're going to start out by assuming that we have a random sample of size n, where each of the elements are IID, meaning identically and independently distributed, and in this case we're going to assume that they're distributed normal with mean mu and variance sigma squared. Now, one thing to note, whenever the normal distribution is given, I've seen it given both ways, either with the standard deviation or with the variance, and notice it really doesn't matter which one you're given as long as it's clear which one you're talking about. Alright, so again, and that's what we're going to assume here in this section. And so we're starting by considering that we've got that normally distributed. So the first theorem we're going to look at says let y1 through yn be IID normal mu sigma squared, then y bar is distributed normal with mean mu, and here this is going to be with variance sigma squared divided by n. You may have also seen this as y bar is distributed normal mean mu with standard deviation sigma over the square root of n. It doesn't really matter which way you use as long as it's clear if you're parameterizing using the variance or the standard deviation. And so you have probably seen this fact before in your intro stat course, in particular when you created confidence intervals or hypothesis tests for the sample mean. And then we have a fact that comes from this. It says let y1 through yn again be IID normal mu sigma squared, and then if we consider z, which is equal to this value here, z is then distributed normal 0, 1. So all we're doing here is we're actually standardizing y bar. We are subtracting off the mean and we are dividing by the standard deviation, because notice if we have y bar minus mu divided by its standard deviation, which is sigma divided by the square root of n, that is the same thing as pulling the square root of n out to the front. Alright. So let's look at an example of how we could apply this. So suppose that systolic blood pressure of a healthy adult males is normally distributed with mean mu equal to 113.8 and standard deviation equal to 10.8. Suppose we take a random sample of 13 healthy adult males and we measure their systolic blood pressure. And then we're going to use this information to find the probability that the sample mean, so notice we're talking about the probability of the sample mean, not the probability of individual observations, will be within 5 of the population mean. So notice here we have the following. We're going to have a sample of size n, so we've got y1 through yn, and we are going to assume that they are IID and they are distributed normal with mean equal to 113.8 and sigma, or the standard deviation, is equal to 40. Alright, so using that theorem we know the distribution of y bar, so notice that y bar is distributed normal with mean 113.8, and then if we wanted to write the variance of y bar, so in other words sigma squared divided by n, that would be equal to 40 squared Sorry, I've written the wrong value here. I just realized with that 40, it's not 40, it is 10.8. So let me fix that. So here we're going to have 10.8 squared divided by n, which in this case, notice we're taking a random sample of 13, so that is divided by 13. And then I put that in my calculator and I got 8.9723. Alright, so now that we know the distribution of y bar, we could find the probability that y bar takes certain values. So in particular, we want to find the probability that y bar is within 5 of the population mean. So this means the following. Saying that y bar is within 5 of the population mean is equivalent to the following probability statement. Or we could say the following. Either of these are the same. So notice what we could now do is, since we know the distribution of y bar, we could use this to find this probability. So there's two different ways that we could do this. We could work with the distribution of y bar, but that's going to be a little bit more difficult here because notice we do have that unknown value mu. So one way to take care of this would be to subtract mu off throughout. So this is going to be the same as the probability that y bar minus mu is between -5 and 5. And now the piece that we have in the middle, which is the random piece, we don't know the distribution of y bar minus mu, but we do know the distribution of y bar minus mu divided by its standard deviation. So now what I'm going to do is go through and divide by the standard deviation of y bar. And remember, the reason I'm taking the square root here is up here I parameterized y bar by using the variance. Okay. Now notice this middle piece. Since we have standardized y bar, we know that middle piece follows a standard normal distribution. So this is the same thing as the following. And notice we could find now what this probability is using R. So way back earlier in the course, we learned about the P norm and the Q norm functions in R. Well, we can use those to find the probability that a normal random variable falls between two values. And in this case, since we're working with Z, that'll be a normal distribution with mean 0 and standard deviation 1. And if you put that into R, you should find something close to the following. So we have about 90.5% is our probability here. All right. Suppose we would like the sample mean to be within 5 of the population mean with probability 0.9. How many healthy adult males must we sample in order to ensure this degree of accuracy? Well, if we go back to the previous problem, notice it's kind of asking the same question, just in the opposite way. Here we were given the sample size of 13 and we found the probability. And here we found that this probability is very close to 0.9. So I already know, just based on part A, when I solve this, I should get something fairly close to 13. So let's see if we do in fact get that. So notice in this case, when we write out our probability statement, we want the following. We want the probability, if we have mu minus 5, less than or equal to y bar, less than or equal to mu plus 5, we want this to be equal to about 90%. Okay. So doing the same thing we did before, I'm going to subtract off mu throughout. And then we know that if we standardize y bar, it will follow a standard normal distribution. So I'm going to divide through by the standard deviation of y bar. And so that's going to give me the following. So now I know that this middle piece is Z. And then we also know sigma from the previous problem. And notice, similar to what we saw before, what I could do to make this easier so I don't have, a fraction in the denominator of a fraction, I'm actually going to write this way instead. So now what I need is notice that these endpoints are the same with the exception of the negative sign here. So really what I'm thinking of in terms of my standard normal distribution is if I draw my standard normal distribution, I know that the probability that z falls between these two endpoints, so in other words, if I had a negative endpoint and a positive endpoint, I know that this area in the middle is equal to 0.9. And if I can find what these two endpoints are, then that's going to tell me what to set these two values, this one and this one, equal to. And so we know that these endpoints we could either use r, or this is one of those common endpoints, is equal to 1.645. So therefore, what we do is we set the square root of n, 5 divided by 10.8, equal to 1.645, and then we solve for n. So in this case, we get that n is equal to 12.625. But remember, this is a sample size calculation, and we always round sample size calculations up, so we know that we need at least 13. And so notice this does match with part A. Alright, so here's another theorem. So if y1 through yn are IID normal mu sigma squared, and z is equal to the following, so notice here we've got yi minus mu divided by sigma. One thing to notice, this is different from what we just saw because before we were standardizing y bar, not y. Here we're standardizing the individual y's, so that's why we just have sigma in the denominator. Oops. If I can get that to be removed. There we go. All right. So then what we're going to do is we're going to square the zi's. So notice this a that I have here is equal to the sum I equals 1 to n zi squared. Then it ends up that the sum of the zi squared is distributed chi-squared with n degrees of freedom, where n is equal to the number of y's, or the number of random variables that we are summing over. So notice we're summing over the y's standardized and squared. And so just as a reminder, we have a picture here of a chi-square distribution. So for example, suppose that z1 through z10 are IID normal with a mean of 0 and a standard deviation or variance of equal to 1. So what we're going to do is we're going to sum those 10 standard normal random variables squared. So we know by the previous theorem that this is going to be distributed chi-squared. So in other words, we know that if we let w be equal to the sum I equals 1 to 10 zi's squared, we know that this is going to be distributed chi-squared with 10 degrees of freedom by that previous theorem. So if we want to find this probability, we need the following. We need the probability that w is greater than or equal to b is equal to 0.95, and again that is with 10 degrees of freedom. So if we draw a picture of a chi-square distribution, we're looking at the following. So we want sum b so that the area above it is equal to 0.95. And so again, if you'll remember, we use those p and those q functions in R. One helps us find endpoints, one helps us find areas, and we saw that we could work with a chi-square distribution. So if you go and you use those in R, you will find that b is equal to 3.9403. All right. Next, find the b such that the probability of the sum from I equals 1 to 10 of zi squared is now less than b is equal to 0.1. So again, just like before, we know the following. If we let w be equal to that sum from I equals 1 to 10 of those zi squareds. We know this is going to be distributed chi-squared with 10 degrees of freedom just like before. So if we draw our picture, we've got our chi-squared distribution. Notice what we're saying is now when we look at our end point B, we've got point 1 to the left of it. And so again, you could use R to find this, and you would find the following. So anytime that you're looking at the sum of standard normal squared, automatically think chi-squared distribution. And so this is one that you probably don't know from your introductory stats course. You know, we see the one where we look at the mean, or the sample mean rather, minus its mean divided by its standard deviation, but this is one that we use, but we don't really see that often. So anytime you see a standard normal squared and you're summing over them, that is going to be distributed chi-squared. Alright, so we've discussed the distribution of y bar, so now let's look at the distribution of the sample standard deviation. In other words, we're looking at the distribution of s squared. So recall that s squared is equal to 1 divided by n, the sum of the yi minus y bar squared. So if we want to find the probability distribution of s squared, recall that Theorem 2 states the following. So this is the one that we just looked at with the sum of the zi squared. So we know that if we have the sum of the zi squared, and notice that yi minus mu divided by sigma is a standard normal, that would have a chi-squared distribution with n degrees of freedom. But what we need to do in order to make that look like s squared is we have to replace mu with y bar. Now the proof of this I'm going to omit here, but generally what happens is since we're estimating mu with y bar, what's really happening is we lose a degree of freedom, and so that gives us this theorem that we have here. If y1 through yn are IID normal with mu sigma squared, then notice here what we've got. We've got 1 over sigma squared times the sum I equals 1 yi minus y bar squared is equal to the following. So we've got s squared divided by sigma squared, and then the whole thing multiplied by n minus 1. It's going to have a chi-squared distribution with n minus 1 degrees of freedom. And then you can also show that y bar and s squared are independent of one another. So next we're going to look at, well, how could we use this information? Alright, so suppose that systolic blood pressure of healthy adult males is normally distributed with mean mu equal to 113.8 and standard deviation equal to 10.8. So this is that example we saw earlier. And suppose we're going to take a random sample of 31, so we've changed n for this problem, healthy adult males, and we're going to measure their systolic blood pressure. We want to find an interval that will contain s squared with probability 95%. So in other words, we're not finding an interval for the mean, we're now finding an interval for the variance. And so we can actually use that distribution that we just saw to help us do that. So the idea here is we want the following. So we're trying to find this interval for s squared. And again, we're going to use that theorem that we just saw. So we know the following. So we know the distribution of n minus 1 s squared divided by sigma, but the value that we're interested in is just s squared by itself. So we're going to see if we can do some manipulation so that here in the middle of the probability we have the piece that we know the distribution of. So let's see how we can do that. What we're going to do is we're going to let w be equal to the following. So w is going to be equal to n minus 1, and remember n in this case is equal to 31, so we're going to have 30 s squared divided by 10.8 squared, which is sigma squared. So notice what I've got here. In the numerator, I've got n minus 1s squared divided by sigma squared. And so I know that this is going to be distributed chi-squared with 30 degrees of freedom. And again, that is because n was equal to 31 for this example. So keeping in mind, again, what we want we can do is we can multiply through by that 30 divided by 10.8 squared. So this is going to be equal to the probability that 30 B1 divided by 10.8 squared is less than or equal to 30 S squared divided by 10.8 squared less than or equal to 30 B2 10.8 squared. So now, and again we're setting that equal to 95%, we now know the distribution of that middle piece. So this is going to be a reoccurring idea when we work with statistics. There'll often be a statistic that we're interested in a probability statement for it, but by itself we don't know its distribution. But what we can do is we can manipulate the probability statement so that in the center we do have something that we know the distribution of. So again, notice we know the distribution of this piece. So if we think of what our chi-square distribution looks like, we would have the following. And again, we're going to have 30 degrees of freedom. So if I work with a chi-square distribution that has 30 degrees of freedom, and what I want to do is I want to find the two endpoints. I want to find a chi-squared endpoint that has 0.975 area to its right and the endpoint that has 0.025 area to its right. So in other words, I'm placing that 95% in the center of the distribution and the 0.025 equally in the two tails. So if I do this, then I'm going to get two endpoints, and then I can equate the two endpoints that I have up here to find B1 and B2. So in order to find what these endpoints are on my chi-square distribution, again, I'm going to use R to help me do that. Alright, so using that Q chi-squared function in R, we find the following. We find that the chi-squared endpoint with 0.975 to its right is equal to 46.98, and the endpoint with 0.025 to its right is equal to 16.8. So now we have what we need to solve for B1 and B2. So for example, to find B1, we're going to set 30 times B1 divided by 10.8 squared. We're going to set that equal to 46.98. And I just realized I've done something silly here, so let's fix this. To erase this. Looking here at my picture, obviously 46 is not less than 16.8. These should be flipped. Alright, now that we have these in the correct order, now we could solve. So now we solve for B1. So this is going to suggest that B1 is equal to 65.32. And then you could do the same thing and solve for B2. And you would get 182.66. So this means that this is the interval that would contain S squared with probability 0.95. And so again, the big idea is you start out with the probability statement using the statistic that you want here, but then we have to manipulate it to something that we know the distribution of, which is what we did here. so we have some more theorems here to look at. So recall from Theorem 1, if we let y1 through yn be IID normal mu sigma squared, then we have y bar is distributed normal mu with variance sigma squared divided by n. So this tells us that z is distributed normal 0, 1. However, we don't usually know the value of sigma. We often have to estimate it from S, and you can show that once you replace sigma with S, you actually no longer end up with a normal distribution. You end up with something that is distributed as a t distribution. And so it has a t distribution with, a student t's distribution with n-1 degrees of freedom. So here is our formal definition of the t distribution. So suppose that z is distributed normal 0, 1 and w is distributed chi-squared with new degrees of freedom. Then if z and w are independent, then we have the following. So notice the t distribution is actually defined as the ratio of something that is distributed as a standard normal divided by something that is chi-squared divided by its degrees of freedom and then the square root. So one thing to keep in mind as you think about the relationships between different distributions, some distributions are defined as some combination of random variables from other distributions, and so we see that with the t distribution. It is defined as the ratio of something that is distributed standard normal divided by the square root of something that is distributed chi-squared divided by its degrees of freedom. And so here's a fact: if y1 through yn are IID normal mu sigma squared, then if t is equal to the square root of n times y bar minus mu divided by s, again, that's going to have a t distribution with n-1 degrees of freedom. So in BST 676, we would actually prove this, but for this class, I'm just giving you this relationship. And so for a t distribution with new degrees of freedom, we have the following. Its expected value is equal to 0, and that shouldn't be too surprising because we can see that it is constructed using a standard normal distribution. Standard normals are centered at 0, and that's where that's coming from. And then the variance is equal to nu divided by 2. And then since the variance is equal to that is going to be greater than 1, so the t distribution has a larger variance than that of the standard normal distribution. Alright, so let's look at another example here. So suppose it's known that GPA of freshmen are normally distributed with mean mu and variance sigma squared. Suppose that it would take a random sample of 8 freshmen. So notice we've got n is equal to 8. We're going to find the probability that the sample mean y bar will be within 3s divided by the square root of 8 of the true population mean mu. Alright, so for this particular example, we have the following. So we have that y1 through y8 are IID normal mu sigma squared, and we want to find the following probability. So rewriting this probability statement, we have the following. And then next thing I'm going to do is I'm going to multiply both sides by the square root of 8, and I'm going to divide both sides by s. And notice the reason that I want to do that is, again, I know the distribution of y bar minus mu, I don't know the distribution of y bar minus mu based on our theorems, but what I do know is this distribution right here. So I'm going to try to make it look like that. And so you can show with a little bit of algebra, you end up with the following. And then since y1 through yn, in this case y8 really, are IID normal mu sigma squared, then, using that theorem that we've got up above, t, which is equal to the square root of n, y bar minus mu divided by s, which, notice, that is really the square root of 8 times y bar minus mu divided by s. That's going to have a t distribution with n minus 1, which in this case n was 8, so this is 7 degrees of freedom. So if we want to find that distribution, what we're going to use is a t distribution. So we started out with that probability that we're interested in. We manipulated this to something that we know the distribution of, and we found that that was equal to the probability that t was between 3 and -3. Well, again, we could use r to help us out here and to find this probability. So the idea is, if we were to look at a t distribution where we had a t with 7 degrees of freedom centered at 0, if we looked at the area in between 3 and -3, and again, you would use r to help you do this, you find out that's approximately equal to 0.98. So one thing to note here is if we did know sigma, then we could use a normal distribution. So just for comparison, if sigma were known, and you could use a normal distribution, so in other words, you know, we weren't having to estimate what sigma was equal to, you would find that this probability was equal to approximately 0.9978. And so the idea here is the t distribution has more variability than a standard normal distribution. So if you were to overlay a z or a standard normal distribution, what you're always going to find with the t distribution is the t distribution is going to have slightly wider tails, and the peak is going to be slightly lower than the z. And again, this is because we do have to preserve the total area under the curve being equal to 1, but the t distribution is going to have slightly more variability. Now, as your sample size increases, so as n approaches some large number, the t distribution is going to get very close to a standard normal distribution. Right? So now, suppose that we have two normal populations and we take two independent random samples. That is, suppose there are two independent random samples, so we're going to call them y1 through yn and x1 through xn. You can use the ratio of the variance from the first over the variance of the second to make inference about the ratio of the two population variances. So what is the probability distribution of s1 squared divided by s2 squared? Well, let w1 be distributed chi-squared with new 1 degrees of freedom, and w2 be distributed chi-squared with new 2 degrees of freedom. It ends up, this is actually where an F distribution comes from. So notice that when we talk about an F distribution, what we're really looking at here is the ratio of two chi-squared distributions divided by their corresponding degrees of freedom. Think back to when you first learned about an ANOVA test. An ANOVA test is really looking at the ratio of two different types of variability. So when we really start thinking about sampling distributions, we know when we talk about variability, we're looking, at chi-squareds. So if you're looking at the ratio of two types of variability, you're really going to be looking at the ratio of chi-squareds, and that's actually what leads us to an F distribution. So this really gets at the idea of when you perform an ANOVA test, which is looking at the ratios of variability, why that test statistic is an F test statistic and comes from an F distribution. Right? And so then we have another fact here dealing with that. So this leads us up to one of our big ideas, which is the central limit theorem. So up until this point, we have assumed that our underlying population is normally distributed. And so the question is, well, what if that isn't the case, and most of the times it isn't? Can we still use some of these things that we've learned about? And the answer is yes, and it all relies on what is known as the central limit theorem. So what is the probability distribution of y bar? if we don't know what the distribution of the y's are, we only know what their expected value and their variance is. So recall, we already showed in Module 6 that we know what the expected value of y bar is and the variance of y bar, and in finding that expected value and that variance, we didn't rely on its distribution. So we already know that this is true. The expected value of y bar is mu, and the variance of y bar is sigma squared divided by n. But notice, neither of these facts tell us anything about the actual distribution of y, just its mean and its variance. So the central limit theorem tells us the following. If we let y1 through yn be IID with the expected value of y equal to mu and the variance of yi equal to sigma, so again, no assumptions on the distribution other than that they're IID, then if we let u sub n be equal to the following, so notice here we are still standardizing y bar just like we did before. Then as n increases, so as our sample size increases, it ends up that the distribution of that function mu n is going to converge to a standard normal. So we get something similar to what we had before, but before, if we know that the y1 through yn are normally distributed, we don't have to rely on what are called asymptotics. We don't need a large n, it holds for any size n. But if we don't know the underlying distribution of the yi's, then we do need a large sample in order for y bar to follow that normal distribution. So as a general rule of thumb, n greater than or equal to 30 is generally used. I've seen textbooks use 20, 25, 35, 40. I mean, that really is just an estimation. And one of the things that we're going to look at in lab next week is we're going to see, okay, when is that rule of 30 good? And what you're going to find out is it's going to depend somewhat on what that underlying population distribution is. If your underlying population distribution is heavily skewed, then 30 might not cut it. And so we're going to actually do some simulations to get a better feel for where does this rule of 30 come? Is it really a good rule? Should we think more critically about it? All right, so let's look at an example here. Alright, so the average gasoline consumption of all families in Rocktown is 16.9 gallons per week with a population standard deviation of 3.2 gallons per week. What is the probability that the mean gasoline consumption of a random sample of 50 families exceeds 16.3 gallons per week? So the first thing to notice here is our n does equal to 50, which is greater than that rule of thumb of 30, so we are going to be able to apply the central limit theorem. Now we know the following. We know that y1 through y50, they are IID with mu equal to 16.9 and sigma equal to 3.2. We do not know the underlying distribution, so this is why we have to rely on the central limit theorem if we're going to make any assumptions about the distribution of y bar. So what we're interested in here is the probability that y bar exceeds 16.3. And notice that is the same thing as the probability of y bar minus the mean divided by the standard deviation divided by the square root of the sample size is greater than, and now I'm going to do the same thing on the other side of the inequality. Notice we know the distribution of this piece right here. So by the central limit theorem, this is equal to the probability that z is greater than negative 1.3258. And then again, just like we saw way back in a previous module, we can use R to help us find these probabilities. So this is equal to 0.9082. Okay, we've got one more example here. The director of a fitness center has determined that the mean and the variance of the amount of time members spend at the fitness center per week are 15.1 and 4.84 hours respectively. Suppose the director randomly takes a sample of 35 members. Find the probability that the total amount of time spent at the fitness center that week for these 35 members exceeds 200 hours. All right, so for this one, we know the following. Now notice the question here is really in terms of total amount of time spent. The other thing is we are going to have a sample of 35. Again, that exceeds our rule of thumb of 30, so we're going to assume it's okay to apply the central limit theorem. So really what I'm interested in here is the sum of the yi's, and I want to show that that sum exceeds 200. That's really what I want to prove. But I don't have a theorem, up above, or at least in our notes, that tells me about the sum of the yi's. I do have a theorem that tells me about the probability of the y bars. So notice what I could do is if I divide both sides of my equation by 35, now I'm working with the probability of y bar. And then we're right back in the spot like we were in the problem that we just looked at. So this theme keeps on reoccurring. What you want to do is start out with the probability of what you're interested in and then see if you can manipulate that probability so you end up with something that you know the distribution of. And so I'm going to leave you to try this on your own because, like I said, it's just like the previous problem. And I believe you should get a probability equal to 0.0495. If you don't get that answer, or you'd like to see the work for that answer, please let me know, and I'll be more than happy to look at that with you. But this is going to conclude this note set.